This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology.
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University.
Sometimes nanotechnology sounds like science fiction before it becomes science fact.
Our guest today is Dr. Julia Kalow, and she knows quite a bit about both these worlds, fiction and nanotechnology. She's a Northwestern University chemist who also studied creative writing.
We welcome her to the show today to hear about her research and her unique perspective on how storytelling and scientific discovery intersect.
Julia is the Dow Chemical Company Associate Professor in the Department of Chemistry here at Northwestern and a member of the IAN. Julia, welcome to the show.
Thank you so much for having me.
So when you were an undergraduate, take us there. You're studying chemistry and creative writing. At the time, did those feel like kind of two separate interests, or did you sense there was a possible connection between them? And how did you end up with both?
I went into college knowing that I really liked writing. That was something that I'd loved all throughout high school, but I didn't necessarily see it as a practical career path. So it's something I wanted to continue doing. And then really, when I took chemistry, it was more of a surprise to me how much I enjoyed that. And being in the research lab for the first time really was what convinced me that's what I wanted to do.
Creative writing, has that played a role in how you think about science today?
For me, really, writing is thinking. So often when I'm writing a proposal, that's when I'm really working through the ideas, the act of writing it down. One thing is that I look for some of the same things in research that I do in fiction, which is to be surprised. So for me, any result that surprises me or that strikes me as being counterintuitive, that's always going to be the most fun to follow up on.
Some of the stuff happening right now in nanoscience is almost like turning something that once felt like alchemy or science fiction into something that's predictable and testable science. What breakthroughs do you think best capture that transformation?
Yeah. So as preparation for this podcast, I actually went and read science fiction novels that, at least according to generative AI, were included nanotechnology. So one of the books I read, Blood Music by Greg Bear, which many sources called this really the first science fiction novel about nanotechnology, which I thought was interesting because never in the book does he use the phrase nanotechnology. But it's about this scientist who takes his own lymphocytes and engineers them to have intelligence and then injects them back in himself. Because it's science fiction, of course, everything goes wrong. They, basically achieve collective intelligence and take over North America.
Okay, yeah.
But that idea of taking cells out and reprogramming them really reminds me of CAR T therapy, right? The cancer therapy where people's immune cells are actually extracted and then genetically engineered so they'll target cancer cells and then re-injected back in the patient, which is fascinating because that really the earliest advances in CAR T therapy happened 2 years after Blood Music was published.
Whoa.
So I think that's a cool example.
He was onto something there.
Yeah, I don't think the scientists were reading that book necessarily, but clearly, there's threads.
What struck me when I last read it was almost unsettling at times how it felt, but it never got too technical. I think that's still a story that people read. And why do you think that story lingers, or the tropes from that story are still out there and play such a big role in literature and science?
Yeah, like what some people have called the gray goo hypothesis that has become very prevalent. This idea that if you have these intelligent, self-replicating nanomachines, they are going to take over the world. Seems like a common trope. So I agree that maybe staying higher level in the world building and in the technology descriptions sometimes maybe increases the longevity of the work, because when the fiction gets too technical, then at least for me as a scientist, it starts to become unbelievable sometimes.
Are you still writing any creative writing today, or is it all just proposals and things like that?
Yeah. No, I like to say that my writing these days is I try to stay in the nonfiction genre.
Yes.
I don't have time to do any creative writing, but I do read a lot. So especially the year I was going up for tenure, I read, I don't know, probably 50 books. It was a really great distraction.
Wow.
That's an insane amount of books. How do you possibly read that many in such a short amount of time?
One a week.
Come on, once a one a week.
It's just
You're on
one
your
a week.
commute. You're relaxing at bedtime, right?
Yeah,
I've been working on Lord of the Rings forever. Oh my God.
Yeah. Well, I mean, if I didn't enjoy something, I would stop reading it. But also I didn't really watch TV, so that was
Yeah.
my outlet. I would say the other way that creative writing or having taken creative writing workshops and classes impacts my practice as a scientist is in how I approach writing with my group. It's very common in a creative writing workshop that everyone takes a turn reading their work and then getting critiques. So that's actually something we do in my lab. We have for manuscripts what we call a group edit, where the first author has to read their manuscript out loud and we go paragraph by paragraph.
Ooh, what's the reaction to that?
It's a little painful, and especially for something long, it can be a lot of reading. For students who don't like writing, it's a new experience.
Or probably something they haven't done since elementary school when you have to go around and read. You're like, yeah.
Possibly.
So when you think about, let's say, today's global challenges, we're talking population growth, aging societies, and limited resources, do you approach your science as kind of problem solving or as a story that needs a new ending?
I'm probably still on the problem-solving side. I think most scientists are, which is not to say that there isn't creativity required. There absolutely is. But it's mostly problem-solving, but also approaching that in an open-minded way and realizing that these enormous challenges require many different solutions.
Some people might be interested to know that imagination does play such a big role in science. I mean, using your imagination and being creative is an important part of the scientific process.
Certainly, and that's something I try to teach when I'm teaching organic chemistry, for example. Especially, I really like to teach synthesis. So the process of learning how to build a molecule through different reactions, and especially trying to teach the students that there is more than one right answer. We often have a synthesis contest at the end of the quarter, and one of the things there is that I tell them there's different ways you can evaluate number of steps, how green the reactions are, things like that. But also part of it is like elegance, or as the kids would say, vibes, right?
The vibes, yes. Let's dive into your work a little bit. How do you usually describe your work to somebody outside of chemistry or nanoscience?
A really big part of my group involves using light. So we like to use light, which provides energy, to actually control the synthesis of different materials, especially soft materials, things like polymers, and also to control their properties. And we use different colors of light to go from something that's softer to stiffer, for example.
You mentioned light, and light shows up again and again in nanoscience and obviously in your work. Your research uses light. You're talking about how to control how polymers form and behave. Now, this already sounds a little bit like science fiction to some of our listeners, but from your perspective, what makes light such a uniquely powerful tool for designing materials, and how is it used in your lab?
So for us, light is so powerful because it is a form of energy that we can introduce non-invasively, right? So compared to thermal energy, where we have to directly heat something, we love the tunability, the fact that by changing the color of light, we're changing the amount of energy we're delivering. And especially for materials, the fact that you can pattern, so you can control where the light goes, perhaps quite precisely, and also when something is experiencing the light, you can turn it on and off. So all of these things we enjoy.
Your lab uses different wavelengths of light to make materials that, they can behave like a rubber band one moment and then silly putty the next. So what's actually changing inside this material when that switch happens?
So it really comes down to the molecular interaction. Since I'm a chemist and we're always interested in building things from the bottom up. So really what's happening is whether those interactions are exchanging very rapidly or very slowly or not at all. I used once the analogy of a square dance, for example. Are people changing their partners very quickly, or are they staying with the same partner? That will change from very quickly exchanging would be more like silly putty where it can flow. Whereas if you're staying with the same partner, that's like a rubber band where you stretch it and you can feel that pushing back against your hands.
Oh, that's a great analogy. You mentioned using the light is so important because unlike using harsh chemicals, you don't need something that is so harsh, like a chemical reaction to trigger these changes, just light. Why is this gentler approach so important when you're working with living systems?
Well, certainly the living systems just can't survive if you heat them above a certain temperature, for example, or if you change the pH so there's too much acid or too much base, you're just going to kill the cells. Same for a lot of the chemicals you might want to add. Living systems cannot survive. Whereas, especially for the longer wavelengths of light, so visible light, especially as you get towards red, those are really quite gentle, so that's important. Certainly UV light is bad, that's why we wear sunscreen. And if you're using UV light, that again can harm cells, but lower energy or redder wavelengths of light can be quite benign. And the other important thing is if you're trying to get get the light through skin, it turns out that, as you can imagine, skin, like does, and your tissues absorb a lot of the light. And that's one reason why you, again, want to use those longer wavelengths of light that can actually penetrate. So if you ever held like a flashlight up to your finger, you may have noticed that it looks red because that's what's coming through.
We've developed also hydrogels whose stiffness can be changed with light, and then, but most importantly, then like changed back. So why is this reversibility such a big deal?
We think that reversibility can be important in biological systems where there's innately some sort of cyclical process. So one example that really inspired me early on was thinking about like the uterus, right? That's something that's changed on a monthly basis. And it also can be useful to be able to reverse some sort of environmental change if you want to be able to mimic the process of, say, a disease state, where often that's, say, with cancer associated with stiffening, and then actually the process of getting better. So say if you have some sort of healing or if you have some sort of therapeutic that can help, say, soften that environment, you want to be able to go both ways, basically.
What was it about the nanoscale that piqued your interest?
Honestly, it came from the fact of being at Northwestern, which is a very collaborative environment, because none of my training really was in nanoscience directly. So coming here and interacting with colleagues, like really my first, you could say, nano paper was with Emily Weiss. So learning about the work Emily was doing with quantum dots and then thinking about, okay, how could we use the molecules that I build, which are actually controlled with light, and then somehow integrate that with her quantum dots. The work my lab does in nanoscience is almost always collaborative because it's really not my background. And something we learned very early on is that when you're dealing with the nanoscale, the tools that we're used to using for molecular scale often don't work. So we found we really need collaborators or else we have no idea what we're doing and what we're looking at and how to look at it. So much is, in my mind, feels less precise because we can't see things with the molecular level precision that we're used to. We're dealing with more complex ensembles rather than a single well-defined molecule. Everything we do has been collaborative, and a lot of it has been looking at how can we take existing nanomaterials. So, for example, Emily Weiss's quantum dots or Mark Hersum's 2D materials, and then impart an extra level of control with our molecules. So especially light-induced control.
Sometimes I learn more from mistakes or failures where things did not go as planned. Is there a situation that you've experienced in your life here at Northwestern or as a scientist where you're like, this did not work at all how we thought it was, but my God, we learned something great?
As an experimental scientist, there are always times when things don't go as planned. For me, it mostly comes up when we try to understand how things are working. We're almost never right about that. So that would probably be the main time where we go in with a certain idea of, oh, this is how this reaction is working, or, oh, this is how the system is controlled. And then once we really delve into it, we realize it's totally different than what we expected.
The surprise ending, if you will.
Yes.
The plot twist. So can we ever expect some science fiction from you someday?
I don't know. If I were to retire and have enough time to write any sort of fiction, I don't know, maybe like a dark comedy of academia.
We need more of those. Yes.
We do need more of those.
Julia, it was wonderful talking with you today, and thank you for exploring this idea of science fiction and how it intersects with the real science that's happening in nanotechnology. Thank you for sharing your time and your thoughts with us today.
Thank you for having me.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.